on-site and virtual participants for sticking with us. So before we proceed, we would like to first extend again our warmest gratitude to the following groups and organizations for making this event even more possible. The Office of the Vice President for Academic Affairs of the University of the Philippines, the National Institute of Geological Sciences, the Society of Economic Geologists, the Geological Society of the Philippines, and the Rush Urgent Working Group. Again, before we begin our hybrid webinar, we would like to remind everyone of some house rules. First, for our virtual participants, may we kindly request you to turn your cameras and microphones off during the duration of our lecturer's presentation. For our on-site participants, you may start asking questions during the presentation of our lecturer. For the virtual participants, questions may be entertained after Professor Hattori's presentation. You can either virtually raise your hand and wait for us to recognize you and unmute your microphone. Quickly, please state your name and affiliation before asking your question. Alternatively, you may enter your questions using the chat box. Again, we are delighted by the presence of Professor Keiko Hattori from the University of Ottawa, who today will talk to us about the mineralization in volcanic arcs. And to introduce our speaker, may I call on Dr. Jillian Ira Gaboracho from the University of the Philippines, National Institute of Geological Sciences.
Thank you, Nico. So good morning, everyone, here on live and on Zoom and on YouTube. So we are at the last day of the World Expert Lecture Series, and it is with honor that I introduce our guest speaker for those who does not know her yet. So Dr. Keiko Hattori is professor at the University of Ottawa in Canada. Her work is mostly focused on geochemistry and ore deposits. So she has studied a variety of mineral deposits and their exploration methods, including epithermal, orogenic gold, porphyry copper, and a lot more. So Professor Hattori is an elected fellow of the Mineralogical Society of America, a fellow of the Royal Society of Canada, and she is also an associate editor of the Nature Scientific Reports and Economic Geology, and she is currently the International Exchange Lecturer of the Society of Economic Geologists. So we are honored to have her here today. Let's welcome her with a round of applause.
Thank you, Gia. So today I am talking about metallic mineral deposits in volcanic arcs. And this lecture is meant for undergraduate students and some graduate students in student chapter. Therefore, there are several diagrams are fairly simplified, and I try to make a shorter presentation today, which allows more questioning discussion time. Okay? So, people knows this is a very, very simplified tectonic map. Sorry, maybe I should say. So people know porphyry copper deposits are present in the island arc and also continental arc, and also epithermal type gold deposit, and also volcanogenic or volcano-hosted massive sulfide deposits. In all these are usually convergent plate boundaries. So today, I will talk about first those deposits formed in a main volcanic belt. And then I will talk about volcanogenic massive sulfide deposits formed in submarine conditions. And then I will talk about epithermal type deposits. Epithermal type deposits are two kinds. One is high sulfidation. Those are associated with porphyry copper. Therefore, I will talk about that first. Later, I will talk about low sulfidation epithermal type deposit. So here, so this is the outline here. So deposit in the main volcanic belt. And I will briefly show those porphyry system, diagram of the porphyry system. This includes shallow part high sulfidation and also some scarring. And then a part 2 is a submarine mineralization in the back arc, volcanic hostile type massive sulfide deposits. And then I'll talk about low sulfidation gold deposits. They form not in a main volcanic belt and not a submarine, of course. They are in a subaerial, in a regional or rift extension setting. So that's I'll talk about in this order. So just first, I'll just explain very important this important thing of that subduction angle. And quite a long time ago, say Ueda 1979 showed two extreme ends of a subduction system, Chilean type, very shallow subduction angle, because those subducting slabs are very young, therefore very buoyant, therefore doesn't sink very, very deep. And then that also very, very, because of very shallow angle, producing those accretional prism. And as I said, a good example is South America, because also ridges are very close to South America. That's the reason that the slabs are young. Another extreme contrasting type is Mariana type. Is Mariana arc. This is a subducting slab. It's very old, more than 220 million years, meaning it's very cold, therefore dense. Therefore, those dense slab makes a very, very steep angle, meaning is that above subducting slab get a tensional environment, and also because of pulling this overlying plate, therefore producing a back arc. So there are also several varieties, just showing how those angles is important. For example, that if the slope is very, very shallow, a bit more wider, volcanism, magmatism, especially when, for example, in Chile, the subduction slab become flat because of those subducting slab, more buoyant. Then those magmatism is very wide. That's very important because magmatism, meaning is providing a heat and magmatic fluid and producing a mineralized hydrothermal system. Okay, so so this is another those extreme is a very, very steep subduction, and a good example is in that Pacific plate. Old one is subducting and very steep, and this is one of those second deepest type think trench, therefore producing a large back arc basin, low basin. Here, because this area is pulled, therefore magmatism back arc, magmatism develop, and lots of submarine hydrothermal activity. Okay. This shows here there's subducting slab, back arc opening, magmatism, and many submarine black smokers. So first, as I mentioned, I will talk about main volcanic belt, what are being formed, including volcanic fronts. Porphyry type deposits. Porphyry is a very important the source of supply of copper, and of course molybdenum, and also that gold is also produced from porphyry type deposits. If you have lots of copper, high temperature, almost always gold is present. So I will show this some Dix-Silitos diagram here, porphyry type deposits, and when that country rocks is a limestone, like Western United States. Skarn may develop. And also upper part, because magmatic fluid separated vapor condense, and a very, very acidic fluid is generated forming high sulfidation gold deposits. So porphyry type deposit, not every deposit has everything, but quite often, for example, porphyry copper deposits associated with epithermal high sulfidation deposit at a shallow level, or sometimes, for example, I will show you later, for example, Papua New Guinea, Ellsberg, those skarn deposit, or Bingham also, skarn is developed associated with porphyry copper deposit. Okay? So first, just I will show those porphyry copper deposits. This is a concentration copper, 0.1 to 1. So fairly low concentration. Because 0.1% of copper, meaning is that chalcopyrite is about 0.3. Meaning is that looks like a rock with a dissemination of copper minerals. And this is a million tons. So this is a billion tons. So just you get the feeling how those maybe deposit is large. Just I made a very, very simple, just some cartoon. If, for example, a 4 kilometer diameter, and if depth is 1 kilometer, volume is 4.2 cubic kilometer, and weight is 9,600 million tons. And so even that is fairly small in this diagram. So you get the idea. Usually porphyry copper deposit, especially large one, is huge. So just a short, oops. What happened? Yeah. Distribution of porphyry copper deposit. As you can see, many porphyry copper deposits are along present day subduction zones. But you notice something strange around here. Kazakhstan, Uzbekistan, Tajikistan, and China. We don't have now current subduction zone because they are associated with Paleozoic or early Mesozoic subduction system. They are very well preserved in accretional prism. Used to be island arc, some are island arc, some are microcontinental. They accrued to the north. And also another old one is here, northeastern part of Australia. They are Paleozoic porphyry copper deposits. And this continent was fairly stable, therefore still very well preserved porphyry copper deposits, but all the others are fairly young. So yeah, sorry that I should have said Paleozoic belt and Paleozoic here, but most are much younger. Actually, Canada looks like in a young subduction zone, but large Canadian deposits are Mesozoic. Again, that it was formed in island arc, accrued to North American continental. So this is just a distribution, and since in the Philippines, everybody knows Philippines has active subduction zones along Manila Trench. The South China Sea plate is subducting, and cluster of porphyry copper deposit in a Baguio area or even south of Baguio area, and also Pinatubo are famous for volcano, but there was several prospect and also Dizon mine in the foothill of Pinatubo, 2.5 million years old. But as you can see, very young, like far southeast is only 1.3 million years. This illustrates porphyry copper deposit doesn't take a billion years or anything long time. Yeah. So So just what are the characteristics associated with shallow intrusions? Singer compiled all deposits are formed less than 3 kilometers in depth. And I'll show you some examples, but when you visit porphyry copper deposit, you see many intrusions in one site or a small area, and they are oxidized. And but then people say, oh, porphyry copper deposits are associated with granite. No, not really. Granitic rocks, meaning is a ferrous. But when you look at lithology, most of the things, as you can see, quartz, alkali feldspar, this is a very well-known classification of rocks. Many deposits are more right side plagiocrete side. As a matter of fact, for example, Central Asian orogenic belt, almost all are diorite. So, but this illustrates many different lithological units can be host for porphyry copper deposits. Okay? But all are fairly ferric to intermediate. So as I mentioned, those porphyry copper deposits, when you visit there, you see many intrusions into that one site. So what kind of geological tectonic setting allows this kind of multiple intrusion of magmas into shallow level? This is just some examples. Bingham Canyon, they produced 30 million tons of copper, one very large porphyry copper deposit, and also actually largest gold producer during that time. And of course, people know Nevada gold, California gold, but actually Bingham Canyon was the largest gold producer because large. And this shows several of those intrusions in that Bingham Canyon. They recognize more than 24 those different units. As you can see, some are monzonite, some are monzonite porphyry, some are quartz monzonite porphyry, I think latite porphyry, quartz latite. So many different lithological units intruded into one site. Yeah? And just later I'll show you about this one. This is a Paleozoic limestone, Mississippian limestone, therefore skarn developed. So using very fortunately some valleys, those volcanic rocks are very well preserved. Using strike and the dip of those volcanic rocks, we could estimate what kind of those magmatic center we did late 1997 and early 2000, and we realized, wow, the site of mineralization was also the top of this paleo 38 million years ago, ancient volcano. And this was more than 4,000 meters high elevation. So it was quite a big volcano when this mineralization happened. So all those intrusions, lots of intrusions, and all very similar, less than 1 million years, and also magmatic hydrothermal activity. So lots of intrusion, more than 20 intrusions, and the magmatic hydrothermal activity, mineralization, all happened in a fairly short time. I can skip, but also this one just shows another example. Western United States, for long time subduction. The timing of the mineralization is only when compressional regime started by flattened slab called Laramide period. So during a usual subduction. Nothing, well, nothing is not a good word, but lots of magmatism, but no porphyry mineralization. Mineralization happened when slab was flattened and more wider magmatism inside, slightly more compressional regime. That is the time mineralization happened. And yes. Okay. Same thing in Chile. And usual subduction and slightly started to have a flattening, therefore wider magmatism area. And then this Nazca plate flattened to form then magmatism compression, because this is a buoyant slab. Therefore, that made more uplifting and flattened, and meaning is that this area become more compression. That is a good environment for porphyry kappa mineralization. And okay, so again, so magmatic fluid is now produced from magma at a shallow level, separating in a vapor, liquid, and liquid is a brine, vapor is a vapor, low density, and those brine produce very high temperature alteration, and outside is a bit cooler, therefore more cooler alteration minerals is produced. And what happened upper part of a porphyry system? But actually, do you have any questions so far? Talked about the geological setting. No. Fairly straightforward. Okay. So now I will talk about what happened in the upper part of a porphyry system. Now magmatic fluid separated saline and the vapor. High temperature at a deep level, HCl is molecular, but then low temperature, HCl dissociates to very acidic solution. So this just illustrates, this is a critical fluid, shallow level, about less than 2 kilometers, starts to separate, could be 1.5 minutes, starts to separate liquid and vapor. And this vapor, like we saw, and this vapor is very, very light, because the vapor is a very low density. Therefore, try to go up, and therefore even cool temperature cools to make a very strongly acidic fluid, and also condensation happened for vapor. Okay, so now here, very acidic fluid in the upper part. Very acidic fluid, meaning is acidic fluid can attack feldspars, hornblende, whatever in igneous minerals. Only what is left is quartz, because solubility of quartz is high in alkaline solution, acidic solution very low. So now upper part, you have vaggy quartz with lots of silica, but nothing else, and acidic alteration mineral, like alunite and or kaolinite, the form. And okay, so these deposits are called high sulfidation epithermal gold deposits. And vapor condensation produce acidic fluids and alunite, pyrophyllite, and sometimes native sulfur. And because so close to the surface, iron oxide forms And also, in this lecture, I didn't talk about, but sulfur is partitioned to vapor phase, and therefore lots of sulfur in a fluid, and also arsenic. Therefore, energite chloride are formed in the upper part. They are all very low temperature mineral, not high temperature mineral, unlike porphyry copper deposit. And for example, porphyry copper deposit, this part have a bonite chalcopyrite. No, not here. Here is only low temperature stable minerals. For example, chlorite may be formed even less than 100 degrees. So this is very well illustrated. For example, Mankayan district in Luzon, quartz alunite very well exposed top of a mountain. Because quartz is very resistant against erosion. Quite often, such high sulfidation baggy quartz are exposed in some topographic high. And so this is a boundary of a volcanic crustic basement and basalt pyroclastic rocks. Actually, this lithological boundary was a bit important. The reason is those vapor went out, and those vapor condense, become a solution. Solution likes to move along gravity. So developed a big alteration along this base. I think I removed that one. I'm really sorry. Okay. So, so far, no questions. No questions. Everything is so simple. So now, I will talk about scaling. This will not be a major part of my presentation, but do you remember this schematic diagram by Dixerito and several continental arc? Like, for example, also Western United States. Many porphyry copper deposits are hosted by those Mississippian country rocks, is Mississippian limestone. So you need to imagine this magma hot. Now this is a limestone. So reaction happens, producing skarn. This is just a cartoon showing limestone here, and with the heat, calcite recrystallized to marble, and then also igneous rocks. Magma produce magmatic fluids. Therefore, those magmatic fluids react to limestone, producing those calcium-rich, because calcium is coming from marble, and calcic silicate minerals, skarn minerals. Okay? I don't go into detail, but sometimes those granitic intrusions and limestone may react. Those skarn may develop inside and the skarn. You can tell because the texture is igneous rocks, but the skarn minerals are present. Okay, so as I said, just skarn mineral is fairly easy for people who took mineralogy because very distinct. Therefore, I don't go into very detail, but just show you those spatial relationship. For example, Erzberg skarn. I'm sorry, that type of skarn. This is adjacent to Grasberg porphyry deposit. Erzberg skarn contains 25 million tons of ore at 2.6, very large skarn. Grasberg is, of course, very large porphyry copper deposit, 2,000 million tons, 2 billion tons of ore, 1.1% copper. This is in an extremely remote place. That's the reason it requires this high very good grade of kappa. In North America, porphyry kappa deposit could be only 0.3, 0.4% kappa. But as I said, remote meaning is everything cost expensive, transport, everything, and also security too. But just I'll show you those where is Grassberg, Ellsberg district. This is Papua New Guinea. This is Papua New Guinea country, and this is Indonesia, and Irian Java boundary is here. And so Grassberg, Ellsberg is located in an Indonesian site. And geographically, this is island, but geologically, this is continent, continuous to Australia. So there are lots of limestones, and this is some photograph I got from mine people, and top of all of those over 4,000 meters high, this porphyry kappa deposit is located. So this just shows those relationship. Grassberg Minas complex here, and this is only 500 meters, so about 1 kilometer or so. And then after those Skarn, Ellsberg Skarn is developed, and Ellsberg high kappa is closer to, of course, the Grassberg in Minas complex. But the Skarn minerals are very widely developed in this limestone because it's such a huge system. Yeah? And all are kind of dioritic in the rocks. Another example is, sorry, this doesn't have a color, but just trying to show, I talked about the Bingham Canyon. This is one of the major porphyry kappa gold deposit in that world, and of course, United States. These solid colored one is zinc, lead, rich deposit developed within limestone. And these are some chalcopyrite, pyrite rich skarn deposit. So I'm not saying a skarn should develop always, no. But sometimes when limestone is country rocks, skarn develops very close to porphyry kappa deposit. Sometimes direction of that fluid or gravity, or therefore only one side has a skarn, but for example, Bingham's cakes, all surrounding area has a skarnization developed, and not only skarnization, but also kappa and lead zinc mineralization. Yeah? So as I said, skarn is very easy to identify because skarn mineral is very, very distinct. Like garnet is always calcium-rich garnet and glossal andradite, and often that they show very nice zoning because the fluid is pulsing, and also sometimes diopside hidden bargite, and rustnite is always developed closer to limestone, and some cases very close to the intrusion. You may have monticelli. This is olivine. We don't know that such olivine exists. Usually we don't hear because olivine is a forestite, ferrite is a magnesium ion. But this environment, lots of calcium, therefore develop calcium olivine. Color, everything is very different from usual forestite, ferrite. And also epidote develops often retrograde stage of diopside hidden bargite, but sometimes epidote may develop after garnet and tremolite actinolite. And also because of very high temperature close to that igneous rocks, graphite may develop, And now that also graphite is one of critical material, and people are also try to utilize such graphite. Yeah. So in the case of that skarn and skarn minerals and also metal, they are kind of a empirical relationship, usually copper skarn and or gold rich skarn. And we call copper skarn is usually, sorry, yeah, usually develops in the garnet skarn. Slightly more oxidized system because garnet can incorporate ferric iron, and ferric iron aluminum is a glossal androidite is a solid solution, and other sulfurylite galena, lead zinc skarn. Usually they develop diopside skarn, meaning is iron is not much ferric, more ferrous, and usually scheelite castrite also usually develop less oxidized environment like a diopside skarn. That is known from empirical relationship. And also those igneous rocks associated with, for example, copper skarn has usually less silica, but almost all the tin skarn, tungsten skarn, scheelite skarn usually has a higher silica content, more granitic. It is again not empirical relationship. It is known, and as you know that European Union publish every year almost what are critical material for our society, especially European Union, but basically for our society. And all those things, tungsten is considered to be very critical. And therefore that now many countries started to have exploration. Okay. So as I mentioned, usually skarn is associated with igneous rocks, but not necessarily surrounding. Basically, where is a limestone, and from where those magmatic fluid is released to limestone area. So sometimes a little tiny branch-like things transport magmatic fluid, making skarnization. Okay? That's all often happens. And unfortunately, garnet is not very photogenic. Or maybe my photography is not good, one way or the other, not great, but just you need to trust me, this is all garnet with some calcifier. Okay. Okay. So usually that, as I said, the magmatic fluid is going out, interacting with the limestone. Therefore, often good zoning and progressively overprinting. That's a very common in skarn. Okay, I think part one is finished. Yes. Yes.
There's a question from one of our participants, Mr. Leo Dagdag, a consulting geologist. This is regarding porphyry copper deposits.
Okay.
So he noticed that PCDs are just few on the southern tip of the African continent. Given that PCDs typically occur in clusters coincident on major structural corridors, and assuming that major players already explored those areas, may he know what's the main reason for this sporadic PCD emplacement? Could it be attributed to no metal budget, volcanic degassing, result to metal loss, or fluid geochemistry? In the tip of the southern of the African continent, in South Africa, apparently there's a PCD deposit. I think he's referring to the map of the global distribution.
Sorry. First one.
I think that's the map, Professor. If you look at the southern portion of the African continent, there's I think a PCD deposit that
Yeah.
our participant is referring to.
And he's asking why or what?
He's asking why, what could be the reason for this sporadic placement of the piece of the PCD in that area?
Okay. I'm not familiar with the porphyry deposit in Africa, so I cannot make a comment or age. I'm terribly sorry about that. But if he can send me some message, then I'm quite happy to elaborate further. What is the age? But we know this is related to also that how to define porphyry kappa deposit. I mean, I need to explain. We know how porphyry kappa deposits are formed. At the same time, people consider disseminated chalcopyrite, disseminated kappa minerals. Then they consider that is a porphyry kappa deposit. And so I am not totally sure this is a real porphyry kappa deposit formed at a shallow level or disseminated chalcopyrite or bonite. And I'm really sorry that I was in South Africa, but I never visited a porphyry kappa deposit in South Africa. But I can imagine that South Africa is not very, does not contain many young igneous rocks, meaning is fairly old, and which geological setting produced such a disseminated kappa deposit. I'm not familiar, so I need to study. And sorry about I did not answer very well. But as I said, I think end of that slide, I like to put my email address. So I'm very happy to answer or elaborate further any of the any questions.
We also have another question from Mr. June Angeles. What is the relationship between the Grasberg and Erzberg intrusions since they are close to each other but not coincident? Different age of emplacement and which one could be younger?
Actually, age-wise, very similar. I have data on my computer, but right now I cannot right away answer. But age is very, very similar. And again, that this particular area had a multiple intrusions, like Grasberg, many intrusions, porphyritic intrusions, holocrystalline intrusions included. Same as Erzberg also. So age-wise is very similar.
Thank you, Professor. How about our on-site participants? Yes.
Good day, Professor Hattery. Since current deposits also produce magnetite or iron oxide minerals, and also some IOCG deposits have been reclassified to skarn deposits. So is it enough to say that the dominant presence of the calc-silicate minerals, the garnet, is it enough that those presence of those minerals can distinguish the skarn deposits from the IOCG deposits?
Well, actually, this is a very good question because many people discussed what is IOC. And as a matter of fact, people become some skarn geologists. I don't put a name of very famous skarn geologist in the world. They become very annoyed because what is IOC? IOC means iron oxide copper. Many deposits contain magnetite. Many deposits contain chalcopyrite. Then, meaning is even porphyry copper. Is this IOC or skarn IOC? Then everything become IOC. And to some extent, when IOC, the terminology of IOC was originally proposed around that in Australia, and it was good because large amount of hematite, magnetite, and chalcopyrite and gold. But now IOC used very, very widely for any iron oxide containing copper deposit. so that's rather create more confusion. And I believe that IOC doesn't have any meaning for this, how they form. So my suggestion is, yes, it's good to describe what kind of minerals. Therefore, yes, magnetite is present, chalcopyrite is present, but I'm not so sure putting IOC solves any question, rather add more confusion.
Thank you, Sensei.
Well, that's a very good question. And also in Ottawa, several students say, oh, I was working on IOC. Oh, I was working IOC. And some are just, simple those disseminated type copper deposit. Some are scarron, some are even at massive sulfide, with a magnetite. Doesn't make any sense. So everything become IOC.
Thank you, Professor. Do we have any more questions for Professor Hattori from our virtual and on-site participants? Oh, we have a comment from Mr. June Angeles. Lithocaps have a silica-rich lower temperature quartz alunite and a lower higher temperature pyrophyllite portion.
Yes.
Why is almost all gold and copper are associated in the quartz alunite and not in the lower clay portion?
This is again a very good question. I think that this is something to do with the solubility of gold. How gold is transported, usually gold HS complex together with the sulfur. And then at but much higher temperature, gold, that was yesterday I showed that much higher temperature, gold is usually transported as a chloride complex. And then at, so shallower level, now alunite is formed, meaning it's no longer H2S. Sulfur is becoming sulfate. So meaning its gold is not transported very well. So it makes sense. Quartz alunite zone, now gold is no longer transported as gold HS minus complex. Therefore, they have to precipitate. Did I answer?
Mr. June Angeles, has Professor Hattori answered your question? Yes.
Yeah, okay, thank you. So I like to talk about also that gold deposit later, because part of 3 is a low sulfidation gold deposit. And so I like to keep, I will start second part. Second part is a volcanic hostile type of massive sulfide deposit. Again, that the terminology, some say volcanic hostile type of massive sulfide. Some people say the volcanic, volcanogenic massive sulfide deposit. So a bit of confusion, but basically the same thing. Whether you consider volcanic rocks is important for genesis or just simply volcanic rock was hosting. That's the reason VHMS or VMS. So now I like to talk about the mineralization in the back arc and VHMS. And present day, there, for example, this is Bonin arc and Mariana arc. And there are many those occurrences of those black smokers precipitating copper, zinc sulfide on a seafloor, actually making chimney. And also other place, very well known, I think in Asia. This is that the Pacific plate is subducting below East China Sea plate, producing this is supposed to be Japanese, Ryukyu arc, and then Bakaku Basin, producing many black smokers. And then those black smokers, actually, some are really large because that when hot water is coming out on the seafloor, right away cooling down, therefore precipitating and making chimneys. Some are more than 5-6 meters high chimneys, and made of such, for example, this is a cut of these chimneys, chalcopyrite, pyrite, sphalerite, and some are tetrahedrite. So what is happening? For example, that the Pacific plate is subducting, and then that the Pacific plate is so dense and old, therefore producing extensional setting, bakak. Therefore, magmatism, heat, and hydrothermal activity. Okay? So Okinawa Trough. So same thing, Lao Basin. Already I showed the Pacific plate subducting and big Bakak Basin, Lao Basin. So this is just showing a distribution of Bakak related some black smoker marine hydrothermal activity, like Lao Basin, Okinawa Trough, what is burning. And the green one is submarine activity, submarine hydrothermal activity along the ridges. And originally I produced several questions because I thought of students, but perhaps you can ignore. But usually ridges, depth is more than 3,000 meters below the surface. On the other hand, for example, that is burning Bakak only 700 meters below the surface, 800 meters below the surface. In Okinawa Trough, for example, is an area 1,400 meters below the surface. That means much shallower. And also that Bakak is a bit more stable. Stable meaning is that ridges keep moving, spreading. Therefore, hydrothermal activity is not stable in some places, more moving. So in that sense, usually Bakak produce larger, those massive sulfide. Yeah? So, and because of shallow depth, people are evaluating whether possible to extract metals. Okay? So also, not only that seafloor, but also on land, there are volcanic fossil type massive sulfide on land. For example, in Canada, many Archean greenstone belts, usually 2.7, 2.8 billion years old, those volcanic rocks host massive sulfide deposits. And also that Sweden and Scandinavian country, those are Proterozoic examples. And also Japan has a very young 14 million, 15 million year old VMS. And also Australia. So many places contain, especially for example, Archean greenstone belt. You find several of those VMS deposits. And so I will show, there's a VMS. It's a very important supply of copper, lead, zinc. And also, as I mentioned, when you have a copper high temperature, then almost always gold is present. And if you have a lead zinc, almost always a silver. As a matter of fact, Canada, Kid Creek VMS is the largest one, and also one of the largest in the world. Therefore, it is the largest silver producer in Canada. So when that deposit becomes large, and then a byproduct become also large. Yeah. And since I'm working in Canada, always a bit emphasis in Canada. So this is that all those VMS, kappa is there, but usually that amount-wise zinc is not major, and of course some are galena, and that's the reason lead zinc. Okay? But as you can see, most of the things, usually VMS is not really kappa rich. Yes, some are kappa rich, but usually among metal-wise zinc. Okay. So for porphyry kappa deposit, I showed those tonnage and the amount of metals. Just showing the same thing now. You see, there now that porphyry kappa deposit, almost all deposit was somewhere 0.1 to 1 around here. But now BMS, most of that deposit are between 1 and 10. So obviously much higher concentration of metal sulfides. Okay? And when you have kappa, usually gold, therefore also some contain about 1 gram or usually less than 1 gram, meaning is 1 ppm gold in those VMS. So therefore very important source of metals. So I don't like a classification, but it's just still that many people use. Therefore, I like to just talk about kappa pyrite type. This was very well described in a cypress. Therefore, people say cypress type. Economically, this is not important, very small. And because usually within that mafic volcanic rocks. And basically, almost all are pyrite and small chalcopyrite. And lead zinc kappa type. This is a very important because very large. Not only Kuroko in that Japan, but also that eastern part of Canada, but also the western part. So this Kuroko type, lead zinc kappa type, found several those subduction zones. And another one is no lead. There is a lead, but a very minuscule amount of lead, kappa zinc type. Often they call Noranda type or Archean type. People believe that the reason why not much lead is maybe related to cluster structure in Archean greenstone belt, because not many sediments, not many felsic rocks. And therefore, this Noranda type is sphalerite, chalcopyrite, or pyrite. Okay? And almost all Archean one is this type. And the phanerozoic one tend to be more like lead rich. So I'll talk about the Japanese example. The reason why is Archean one is very not easy to find a geological setting or tectonic setting. Now we get to know most likely what happened. But in the case of Japan, especially 14 million years ago, we know exactly what kind of geological setting. And also because Japanese one is not metamorphosed. On the other hand, Archean examples are usually metamorphosed. Some are amphiolite grade, some are upper green schist faces. So therefore, no overprinting effect, no metamorphism in that Japanese deposit. So just shows. So there's a Hokuroku area is a very famous Kuroko district, subduction of Pacific Ocean. This was going on since late Mesozoic time. And this area was all actually submarine conditions. And judging from volcanic rocks, we know this was back arc. And many those mass volcanogenic massive sulfide deposits occur in a cluster. And this one is about just over 100 kilometers, but almost all massive sulfide deposits occur within this area. And also that paleotopography suggests this was a large basin or caldera, large caldera structure. Within large caldera structure, many volcanogenic massive sulfide deposits. First of all, how basin developed, how caldera developed, because extension. So this extension in submarine conditions, that was very good because normal fault developed and restrict those ocean circulation. This is a place, and also magma is coming up, producing hydrothermal activity, marine hydrothermal activity. So I don't go into very detail, but they are good zoning usually. And usually those are felsic igneous rocks and some intermediate igneous rocks, and quite often some mafic also volcanic rocks. So basically that bimodal volcanism in this area. Again, not supporting, yes, this was a back arc extension producing bimodal volcanism. Basically, mafic magma came up. And as I said, just not very important, but in a very well preserved place. You can see very copper-rich part, those feeder part, and then that obviously some magmatic fluid was slightly high pressure, therefore brecciation forms, and again the chalcopyrite of copper part and more zinc lead rich part, and finally covered by those barite and also iron hydroxide or iron oxide. So often these iron oxide layer, very chatty iron oxide layer, is a very extensive entire basin. And maybe only just 100 meters, but this one is extended more than 10, 20 kilometers. What happened is that magmatic hydrothermal activity happens, then metal sulfide precipitate zap in a short distance because of heavy. But then at very fine-grained silica, very fine-grained iron oxide, it goes going up. And then at very gradually sinking to the bottom. That's the reason those ferruginous strata layer is very extensive all along the basin and quite often used for exploration. Because if you have this ferruginous strata layer, and if you follow, and then become, if you see some lead zinc, meaning is that is a place where closer to the center of those marine, submarine hydrothermal activity. So this I'm showing. As a matter of fact, when you people are searching for submarine, present day submarine black smokers, what they do is they are cruising, they see some kind of a cloud-like things, kilometer or several hundred meters below the surface. That because these iron hydroxide, manganese hydroxide, and silica is dispersed, making a big cloud. And when you see something, they knew below has something. And this below is usually black smoke. Yeah. So, as I said, that in even Archean terrain, for example, this is very well preserved far away. And actually, I was a bit surprised. Some are this thickness, but continuous. Sometimes very thick, like a meter, but usually very, very thin one is dispersed all in a basin. So ideal zoning, also Archean terrain. Archean terrain doesn't have much lead, and also no barite because ocean water didn't have sulfate much. Therefore, no usual barite zone, no lead, but basically same thing. Brecciated feeder part, chalcopyrite rich, and chalcopyrite pyrite, and going up to more sphalerite. And then this doesn't show, but a very exhalate horizon, so-called exhalating silica-rich chalky zone. But they are not economical, so it doesn't show up here in this diagram. Again, Noranda is in Quebec, very well studied because very good exposure. Very fortunately, unfortunately, Canada had a big glacier. Those glaciers covered soil and grass, everything. And therefore, those slightly topographic high area is very well exposed. Basically, glacier polished up, cleaned for us. No. And so usually chalcopyrite is high in that central part because this is a hot part. Chalcopyrite precipitate, and when the temperature decrease, therefore almost always such zoning. Chalcopyrite is high in the center and low in the upper part and low in the peripheral part. And that gold follows copper, meaning gold is high in the center, gold is low in the peripheral part. And as I mentioned, in that Japan, Kuroko area, many massive sulfide deposit in that basin. Same as Archean Noranda camp. This is same horizon. Same horizon and all covered by thin, those siliceous layer, chalky layer, many these massive sulfide deposit in this Noranda camp. And always there are those brecciated part and also alteration chimney, backward chimney, alteration is below those massive sulfide deposit. Again, that usually silicite, elite, white mica, and also that abundant chloride. And I'll explain a bit because chloride in that massive sulfide deposits are very different from usually green colored chloride. Some of those chloride in BMS, no iron, therefore very white and very magnesium rich in the member. And what happened is, so as I said, Noranda, they believe large caldera formed, and within large caldera, those BMS. Okay, so this is a cartoon showing what happens. Those seawater is there, and because hot magma is coming up, magmatic fluid is ascending. This suck up those because discharge of fluid going upward, some convection system develop, and the seawater is sucked into rocks. Seawater contains a much higher magnesium to calcium ratio than a usual fluid, therefore producing magnesium chloride. Lots of magnesium chloride. And magmatic fluid produce supply potassium, making some elite white mica. And because seawater contains sulfate, and when you heat up seawater, anhydrite precipitate. That's the reason that here some anhydrite or sulfate minerals precipitate. And at the deeper part, their water to rock ratio is much lower, therefore more magmatic hydrothermal related alteration. But upper part, lots of water and the seawater is coming in. Therefore, often lots of those sulfate minerals and magnesium chloride. Those alteration is quite different from like porphyry kappa deposit or other type of, so just to illustrate, this is a long time ago, people did an experiment. When you put, this is a 50 days, 100 days, 150 days, how much magnesium in water? When you have a seawater and even heating up 70 degree, 150 degree, magnesium content sharply decrease in that water, meaning is magnesium entered to rocks, forming magnesium chloride. This is a Jurassic they are rocks below croco type massive sulfide deposits in British Columbia, full of magnesium chloride. So what happens in Archean terrain? Maybe this is not relevant here, but when that not only Archean, when that rocks are metamorphosed, those chloride and lots of silica reacting to form metamorphic mineral like cordierite and phosphorite. Or sometimes, yes, the rocks looks like cordierite and phosphorite make quite a spot. You may know dog called Dalmatianite, spotted. So we call Dalmatianite. Okay. And this is some examples near Thunder Bay. Aluminum is so enriched and magnesium, so forming magnesium, aluminum. Garnet. This is one pillow basalt, one pillow. This is another pillow. All are now you see lots of garnet. Yeah. Again, that metamorphosed terrain, those metamorphic minerals reflect what happened, what elements entered to the rocks. But again, that when you see something like that, you know this is not the usual basalt. This is not the usual pillow basalt. Because why that the usual pillow basalt produces such a huge amount of garnet? And because aluminum is enriched, magnesium is enriched. Okay. Okay. So yeah, I can pick. So condition, you need to have a bit of, because if open ocean, you cannot accumulate sulfide. So you need a shallow heat source to sustain hydrothermal activity. And water depth may be slightly deeper. If too shallow, water boils over and only vapor can come up. So there really a great geological setting is like a basin like caldera. Caldera meaning below have a magma, heat source, and also caldera produce environment to preserve sulfides. Okay, so something like that. I think part 2 finished. Any questions? If no questions, I'll talk about low sulfidation gold deposit. Any questions?
Do we have any questions for Professor Hattori for both our virtual and on-site participants? There's a question from Mr. June Angeles. Where does mafic sediment-hosted Beshi type fit in your VHMS categories? Why are they always metamorphosed like Noranda type?
Not always, because regional metamorphism are different from one place to the other. And the question is nothing to do with that mafic or felsic, more regional setting. Did I read what is the answer? Where does a mafic sediment hosted base type fit into? Oh, okay. I did not talk about a base type deposits because base type deposits is of course that Kislaga in Norway and very different from Croco type deposit and because very high cobalt and but now that in the past, I think 10 years or so, several of those dating using rhenium osmium of those Besh type deposit, they found that mineralization happened very far away in most likely ridge setting or and then during that oceanic subduction, those Besh type deposit accrued to Japan. So what is the actual real geological setting for Besh type deposit? Through that, lots of discussion. So that's another reason I did not talk about it. However, that igneous rocks associated with the Besh type were that oceanic type, oceanic basalts, and very different from a Croco type or Noranda type. Those Croco type, Noranda type are associated with calc-alkaline, some authoritic, but definitely subduction related volcanic rocks. And today's lecture is mineral deposit in volcanic arc. That's the reason I did not include Besh type deposit.
Thank you, Professor. We also have another question from Dr. Jun Yumul. He asked, where would the metal come from? From the magma or from the wall rock or a combination?
This is a good question, and several of those fluid inclusion studies, and also several what was any idea that also sulfide stop studies suggest they are not all sulfur came from seawater, but most sulfur came from magma. And also now that they have several studies of their trace elements or minor elements in the sulfides and quite high selenium, meaning is that strong magmatic components for at least sulfur and the selenium, and probably meaning is the tellurium. And to me, that meaning is most likely copper gold also came from magma.
Thank you, Professor. Do we have any more questions for Professor Hattori?
But regarding the person who asked me about a Besh type deposit, if you'd like to know more about the Besh type deposit, I'm quite happy to provide some information of especially recent information. We are getting a very different view how Besh type deposit is formed, but definitely not volcanic arc.
Thank you, Professor. Any more questions? There are no more questions, Professor. I think we can provide. We can proceed with the next part of the lecture.
Thank you very much. Now the third part of a presentation is low sulfidation gold deposits. Already I talked about high sulfidation type of gold deposit as a part of a porphyry system. So this is a very different. So but before talking about low sulfidation gold deposits, first I need to just explain what are low sulfidation deposits and what are epithermal type gold deposit. So all epithermal deposit formed very shallow depths. This is a compilation of the depth here and the age of epithermal type mineralization. As you can see, most epithermal type deposits formed less than 1 kilometer below the surface. So, and also that I need to show this green one is a low sulfidation gold deposit, and this purple is a high sulfidation gold deposit. So this already, as I said, high sulfidation gold deposit explained as a part of that shallowest part of a porphyry system. So now I'm talking about is a low sulfidation. The low sulfidation gold deposit. This is a vertical section of Habona in a Coromandel Peninsula in New Zealand. They are tilted, therefore paleo surface is now preserved here. And the paleo surface, we see layer of the sinter, meaning is that, yes, that auriferous fluid came up and outflowed to the surface, producing sinter. This is fairly common for low sulfidation gold deposit. So, as I said, some people may be a bit not familiar with low sulfidation, high sulfidation. Therefore, I'll just explain. High sulfidation fluid is here. This is basically activity of sulfur, meaning is more sulfur, and here is less sulfur. This is a temperature. This is 200 degrees, 300 degrees. Most of epithermal type deposit formed about less than 300. But some are going to 350, but anyhow, there's a very low temperature. And there's a high sulfidation fluid because the amount of sulfur is high, producing copperite, digenite, more sulfur to metal ratios. On the other hand, low sulfidation fluid produced, for example, maybe a pyrite, pyrrhotite, or maybe like argentite, silver sulfide. So therefore, mineralogy is a bit different. And also that high sulfidation deposit. This is now looking at oxidation conditions. And this is pH, because of that, trying to show how much, for example, sulfur species, H2S, HS minus, and more sulfate in that oxidized conditions. High sulfidation deposit is a high sulfidation deposit formed under much higher oxidation conditions compared to low sulfidation oxidation conditions. Based on those mineralogy, mineral chemistry, we get to know what are oxidation conditions and sulfur activities of sulfur. So two are very different. And also, as I said, this is formed in upper part of porphyry system. This is low sulfidation, is totally different. So that's I like to explain. So what are the characteristics of a low sulfidation epithermal type deposit? Already I mentioned very shallow. Almost all very big one is very, very shallow. And the texture is very distinct. If you see some hand specimen from of any high low sulfidation deposit, doesn't matter, New Zealand or Russia, Japan, Philippines, or Indonesia, right away you can tell that those are low sulfidation gold deposit because of this very distinct. In many ways, for example, usually banding develops, very, very fine banding, and usually very, very fine grained. And then this is not always, however, often you find those very, very fine grained of silica called colloidal silica. Basically that silica deposited very quickly, did not have time to have a good crystal, and the colloidal silica is formed. And also that lots of drools, because a very shallow level, therefore lithostatic pressure was very low, making some still that open space. And they are very common to have adularia. Adularia could become very fine-grained, or what sometimes very good rhombohedral shape. And also carbonate. Sometimes actually interestingly, carbonate may be preserved, but maybe sometimes if carbonate may be totally replaced by later silica. That's again very common. And sometimes manganese carbonate may develop. And all low sulfidation epithermal type deposit are formed in subaerial conditions. And many fluid inclusion studies show low salinity. This is totally different from volcanogenic massive sulfide deposits. Salinity is low and near neutral pH fluid. That's the reason adularia form, because if acidic, more elite or kaolin. So near neutral pH condition, and from many isotope work, we know surface-derived water were incorporated into hydrothermal systems. This does not mean that no magmatic fluid, but magmatic fluid was a very minor component, and the surface-derived water was quite volume-wise dominant. And also, as I mentioned, when a paleo surface is preserved, there's a sinter is found on a paleo surface. Again, paleo surface is very distinct. You can tell this was a sinter paleo surface. So this is another example. When you do cobalt nitride staining, you see where is adularia, and very, very cobalt nitride makes a very yellow stain for potash feldspar, and a very nice bundle actually. Yeah. And so as I said, sometimes open space filling make a comb textured quartz, and but usually like so. And so this is the center, several of those photograph of a center, and this is a Omui deposit in Hokkaido. They have a more than 3 meter high center deposit, and this is a Fabona, and the center itself, gold content or arsenic content, is very low, but still present. That's also a hint. Yes, this was a part of mineralizing hydrothermal system. Yeah? And oops, what? Yeah. Okay, sorry. Oops, wow. I'm sorry about that. So McLaughlin deposit of California, this had 100 ton gold, and this area has those center, and also this area has several those mercury cinnabar mine, and also that this had lots of mercury, and then because the center, some people consider probably the deeper part may have some deposit, and they pushed, and they found this gold deposit, or sulfidation gold deposit. And again, that very typical low sulfidation gold deposit. Actually, you can turn off air conditioner if you feel cold. So I'm sorry with that. So just I'll show the setting, location of this deposit in California. This is Western United States. Deposit is located here. And I like to show that here is the Joan de Fuca plate, and this area has several small oceanic plate. This oceanic plate, gold plate, is subducting below the ridge, producing Cascadia volcano. Important thing here is McLaughlin deposit is located outside of this subduction related magmatism. And this is based on the range and some external setting. So deposit is not related subduction related magmatism. That's just I like to emphasize. Okay, and then this actually Cascadia volcano is still active, as you know that Mount Shasta and so on. And but this area, this is that gold deposit is here, and there are several bimodal volcanism like Sonoma volcanic rocks and Clear Lake volcanic rocks 2.2 to 0.26 million years. And this gold deposit is associated with this volcanic rocks, not Cascadia subduction volcanic rocks. So it is in a large scale subduction zone. Western United States is subduction zone, but gold mineralization, auriferous hydrothermal activity was not related to subduction related magmatism. And so then people say, oh, why such magmatism? Why all of a sudden such mafic volcanism here? Name is different, but essentially all those are same thing. These are mafic volcanic rocks and several dacitic volcanic rocks. So meaning is that minor rifting happened, therefore producing mafic magma from a mantle depth and partial melting in a crust rocks to produce those bimodal volcanism. Okay? So just showing these volcanism become younger, and then this gold deposit. And Cascadia magmatism is still ongoing. Okay. So, so now from California to that Western Pacific, Japan, because Japan has many actually low sulfidation gold deposit. この前、千歳、佐渡、高玉、伊豆、 either has not one deposit, several. Therefore, the total is at least 47 tons of gold. But almost all, for example, gold deposit like Sado, Chitose Konomai, and Izu were mined more than that 400 or 500 years. Therefore, actual value of the gold is probably more. And just I like to show, this is those volcanic hostile type massive sulfide deposit is green, and this is a submarine volcanic rocks distribution. And meaning is, for example, these are some hostile submarine volcanic rocks. The mineralization event is much later after this become a sub-area. So first I'll talk about Izu, because I'm very familiar. Actually, when I was an undergraduate student, this was my BSc thesis project area. But when you are 20 years old, I didn't realize this is tectonically very active area. And now I start to understand a bit more. So this is there's a volcanic peninsula, and this is a part of Izu-Bonin arc. This Izu-Bonin arc produced because of Pacific plate is subducting along Izu-Bonin Trench above below Philippine Sea plate. So this Izu-Bonin arc is on Philippine Sea plate. But the Philippine Sea plate is moving northward. Therefore, this used to be more than 2,000 kilometers south. They moved to now very, very attached now to Japan. So meaning is this Philippine Sea plate is keep pushing this Izu Peninsula and other those islands to further north. So when this it happened is so about below 2 million years ago, this was a submarine volcano. Because again, at this Philippine Sea plate moved, moved, then collided about 1.5 million years ago. When collide, you cannot just push each other. One part must subduct. Then what happened is this part started to subduct, but also this part had to subduct. So now, after 1.5 million years before, what is happening is now being pushed, and slightly rotated, and position of volcanic front by subduction of Pacific plate moved to more eastern part, and now this is Izu Peninsula. And now still moving, subducting, and therefore no longer arc volcanism, because arc volcanism, subduction related arc volcanism is now here, moved to this part, because this moved further westward rotation. And so now that this area has a monogenic mafic volcanism, and as I said, because moving, subducting here, east part, subducting west part, meaning is that double subduction in this little tiny area. This is incredible. This is 20 kilometers. So therefore, very large tensional setting. And then when we look at those, this is a gold deposit, all those red gold veins. And the gold veins are as you can see, parallel to this one makes sense because subducting, they need to open up. Yeah. And those ages are less than 1.5 million years. Some are 0.76, 1.36, well, anyhow, or fairly young. As I mentioned, those low sulfidation gold deposit formed in a subaerial condition, so not a submarine condition. And originally, as I said, this was way south, submarine volcano. Now colliding starts to become subaerial, and the subduction, double subduction made extension, local, regional extension produced gold deposit. Again, long after subduction-related arc magmatism. Another example is Sado. And Sado, this is located here. And people know, of course, Japan Sea did not exist more than that. More than, for example, 44 million years ago, Japan was connected to Asia. And how do we know? Because those the subduction-related continental magmatism is present in that Korean peninsula. And then at the opening of this Japan Sea by as a back arc opening started. Exact timing is lots of discussion, but definitely over 35 million years ago. And then when you look at timing of gold mineralization is and as I mentioned, the continental arc magmatism was subduction related continental magmatism was for at least 44 million years ago. Then now these gold mineralization timing is very coinciding with the opening of Japan Sea, mafic dike swarms. Obviously, this is not related to subduction related magmatism. And those are lifting. And so again, that Sado gold mineralization, yes, it is in now overall arc, but nothing to do with the subduction related magmatism or mineralization. Okay. So this is a final example is Hokusatsu area, because Hokusatsu area contains Hishikari, kind of world famous low sulfidation deposit. So I have to include this one. And Hishikari has a really high grade gold ore. And many places are more than veins 500 grams per ton. Yes. Again, that Hishikari, well, I think this, yeah. Are you sure this one? Yeah, okay, sorry. Hishikari area. There's Cretaceous sedimentary rocks covered by these andesitic and dacitic volcanic rocks. And this is 0.9 million years. Therefore, this mineralization happened, some part of the mineralization happened younger than 0.9 million years. And the outflow of, this is cutting there. And so let's look at the tectonic setting. Current volcanic front is here. Hishikari is located in a back. And some people consider this is back arc. However, I have a slightly different opinion that what in the past more than 15 years, Japan has been doing a very detailed GPS measurement because they like to know deformation of that crust because if that if a stress is built up, that could be a very dangerous area for next large seismic activity. So then after those very detailed GPS measurement, 1 or 2 years or 3 years, it is difficult to know what kind of really that movement. But now after 10 years, we know what is happening is this subduction of Philippine Sea plate. This main part of that Japan is moving towards China or towards west. On the other hand, here, for example, where nuclear arc is produced, this is moving more southward. And people consider this is maybe related to something to do with this either collided, volcanic arc collided at the main island, producing those movement of the main island to northwestward. But anyhow, so the Hishikari area or Hokusatsu area containing many those low sulfidation gold deposits are located here. Very large tensional environment. And as a matter of fact, several of those thermal springs contain high helium-3, confirming, yes, some magmatic fluid, magmatic volatile is coming up in this area. So, because deposit formed at fairly low temperature, the alteration is a very low temperature also. Kaolin is a small amount of chloride, but usually white mica, elite, smectite, or kaolinite are the major alteration minerals for these low sulfidation deposit. Same is in New Zealand. That's actually just my student finished some alteration work in that Savona deposit. Basically the same thing, elite, smectite. Yeah, Martha vein, elite, smectite are the major alteration here, and that below is usually elite and minor other. So those are main or alteration associated with low sulfidation deposit. I believe that's it. No, okay. Yeah, thematic figures of alteration. And so, because now close to 11 o'clock, time allocated for me is until 11, but of course, I'm happy to answer some questions.
Thank you, Professor Hattori. We have one question from our participant in the live stream. This is from Phoebe Torres from UPNIX. She's asking, is it possible to have a clay zoning in Cyprus type deposit as well?
Clay zoning?
A clay zoning in a Cyprus type deposit. I think she's referring to the VMS or the volcanoes.
VMS. The zoning of alteration. Again, that because seawater was involved, several of those magnesium chloride, but usually Cyprus type. Actually, they, as I said, economically all very small, because rocks are mafic, meaning is more iron also compared to, for example, dacite rocks. Therefore, chloride tend to have a more magnesium chloride as well as a magnesium iron chloride.
Uh, so I have a question. For low sulfidation, I just want to ask what are the parameters to create Guru bonds because these are very fine sulfides and are these also common in intermediate and high sulfidation? Thank you very much.
Which is a common?
The Guru bonds. Guru.
Gingoro band. The gingoro band is of course very common in a low sulfidation and some of intermediate. Yes.
But it's not common or it's very in high sulfidation.
High sulfidation, no gingoro, no. Yeah, texture is totally different. But also that gingoro, the appearance of gingoro is quite different from one place to the other. Sometimes, for example, really very, very faint color. Oops. Yes. Those are very, very faint color gingoro. And but this is more prominent gingoro. But this prominent gingoro is because this particular vein contained 11,000 gram per ton gold and the percent order silver. And doesn't matter where I made a thin section, a polished section, I find the gold grains. So yes.
Thank you, Professor. We have a question from one of our Zoom participants, Mr. June Angeles. He commented that your lectures for the last 3 days are enlightening, but he has one observation. You have discussed HSE and LSE, but somehow did not discuss about intermediate sulfidation epithermals. In the Philippines, ISE is the most common epithermal type, like in Baguio, Victoria Teresa Suyok in Mangkayan, Mako and Koo. And what could be the reason for not discussing ISEs?
Okay. As I mentioned today, I tried to make simplified my lecture in 2 hours, covering porphyric kappa to high sulfidation and BMS and low sulfidation. Therefore, I did not talk about intermediate sulfidation gold deposit. But yes, that I'm aware far southeast area and Lepanto and Victoria and all those area contains intermediate high sulfidation and porphyric kappa deposit. But I did not talk about it because I tried to cover 3 extreme cases. And but the intermediate one is I may have one that yeah, intermediate one is located fairly. Oxidation condition is much higher than that high sulfidation, but actually that intermediate one, my experience, intermediate one, oxidation condition could be quite varied. But sorry, I did not talk about it. Yes. Considering this is a Philippine, I should have mentioned maybe. Yeah, sorry about that.
Thank you, Professor. There's a question from Kurt Linus from LCMC in relation to Mr. Angeles' question. Does this mean that high sulfidation, intermediate, and low sulfidation are not genetically related phases?
High sulfidation and low sulfidation not related at all. For example, I did not mention, but for example, in a Kyushu, Ishikari area is low sulfidation, much younger. High sulfidation one is present in a further southern part of Kyushu, much older, like 4 million, 5 million. So the age is different, geological setting is different, and magma in the case of low sulfidation deposit, whether that what kind of magma is still in a debate and a discussion because it's not very crystal clear. So again, that the geological setting very different.
Thank you. We have another question from JP Fortines from the University of Southeastern Philippines. His question is regarding porphyry copper. Does the size of the volcano have an influence in terms of metals and mineral distribution and fluid flow?
Size of a
The size of the volcano.
volcano. I believe because that if lots of magma is coming up, producing a large volcano. However, not many areas. For example, that Chile, almost all those top part is eroded. Therefore, we don't know exact shape of a volcano. And in the case of Bingham, we are lucky because several valleys preserved volcanic rocks related to volcanic activity. Therefore, we could evaluate what kind of a volcano, Bingham volcano was present. But usually those volcanic rocks is gone. And it's difficult to predict what size of the volcano. But I suspect a very large volcano for large porphyry copper.
Thank you. We have another question from Rahel Santos from the Mines and Geosciences Bureau. Japan, being an island arc like the Philippines, seems to have less or general absence of porphyry copper mineralization relative to the Philippines. What could be the possible reason?
This is a very good question, and actually I wrote a paper why Japan doesn't have porphyry copper deposit. Several reasons. For example, Japan had I think some of the diagram shows that Japan used to be until that over 35 million years ago. Japan was part of that China, and then a Japan Sea opening, and then at the Japan Sea opening produced a large amount of submarine volcanic rocks. And obviously, porphyry copper deposit are not formed in a submarine volcanic environment, and a large area in Japan is a Miocene submarine rocks. That's one reason. Another one is that many there, for example, that very well known high pressure belt called the Sambagawa metamorphic belt. When we look at the Sambagawa belt, we can tell what kind of things may have subducted. It appears a fairly reduced material. So that's maybe the reason, unlike Philippines, that Japan subarc environment was a fairly reduced conditions. If subarc is reduced, you can't produce very highly oxidized magmas for porphyry copper deposit.
Thank you, Professor. Do we have any more questions for Professor Hattori from our on-site virtual participants? Surgeon analyst is asking, could there be copper hidden below the numerous high epithermals? Could there be copper hidden below numerous high sulfidation?
Copper hidden below low
The-
sulfidation or
High sulfidation.
high sulfidation. As I mentioned, that many high sulfidation gold deposit, for example, that usually they are finding some indication of that porphyry copper type deposit. But how large is a different story, because sometimes a very large high sulfidation gold deposit, maybe that below is very small. Or how deep, again, that is because if you see high sulfidation gold deposit, the meaning is we are looking at very close to the surface and stuff. So could be more than 1 kilometer below the surface. Because could be a 2 kilometer below the surface, whether it is economical or not. I think that also that yesterday I talked about understanding alteration is very important, and I explained one example of magma deposit, magma mine. This is a high sulfidation type replacement type deposit, and they're trying to do finding more ore. They did exploration drilling, and they encountered quartz silicite rocks. They thought very strange. How come quartz silicite rocks? Because high sulfidation gold deposit doesn't have such quartz silicite alteration. And they looked at more carefully several thin sections and rocks. They found some of the quartz silicite rocks were overprint of potassic alteration. So therefore they knew further deep they are the porphyry copper deposit, and they found resolution porphyry copper deposits. So this is one of the examples. Understanding alteration may lead those discovery. So if you have a good high sulfidation gold deposit, perhaps looking at maybe alteration, if you see something like related to porphyry copper, very promising to find porphyry copper deposit below.
A follow-up question from Sir. That's interesting. So there are signs of porphyry copper near HSEs, but not enough exploration to find economic ones.
Yes, Steve.
So there are signs of porphyry copper near high sulfidation epithermals, but not enough exploration to find economic ones.
Again, like a good example is far southeast and the relationship far southeast and the Lepanto. Lepanto deposit formed kind of a bit of not directly above, and some because those vapor condense moves, and therefore not directly below. Necessarily not directly below high sulfidation is a porphyry copper deposit. So I think that understanding again that terrain, what kind of terrain, what is that perhaps fluid flow that may be important in exploration. I'm not saying definitely should have a porphyry copper, should have a high sulfidation, but it is a possible, very promising, but not necessarily. Always a schematic diagram is high sulfidation directly above porphyry copper, but in a reality, often slightly offset. Just like also porphyry copper and the scan also.
Thank you, Professor. Any more questions for Professor Hattori? So question from Moroso, from the live audience.
Just last question, Sensei. I just want to briefly ask if you really think that green rock mineral chemistry really lead to blind porphyry copper deposits, or is it a good exploration tool to use for further discovering porphyry copper deposits? Thank you very much.
Just yesterday that I showed several of those examples, Kalamazoo's case, all the example, and also resolution is another example. There are many such discoveries. Again, that you need to have good eyes, and also you need to have understanding of what kind of alteration you expect. If you don't know, you observe maybe quartz silicite. So some people don't know, don't have a clue, may say, so what? But after that, taking a mineral deposit course and taking several lectures, then you have a very good understanding to be successful exploration geologist. Yeah.
So thank you. There's a comment. Gaison, he said that there are a number of porphyry prospects in Mangkayan and even within the Lepanto tenement. I think it's a comment regarding your answer for Mr. Angeles' question regarding the high sulfidation and porphyry coppers. So you mentioned that there's a number of porphyry prospects in Mangkayan and also in the Lepanto area.
Yeah. Oh, that's so wonderful because if you have a high sulfidation deposit, meaning is that that the magma was capable to transport a large amount of sulfur. Meaning is that the magma was quite oxidized and capable to transport also metals. So very promising, but promising or fertile magma does not necessarily mean producing deposit. Several other factors are involved. Yeah. But first, we need to have a promising environment, promising magma. Yes.
Thank you. So any more questions for Professor Hattori from our live audience, virtual participants? Mr. Tizon?
Good day, Dr. Rattery. What controls the silver content in epithermal deposit?
Silver contents
Yeah.
are quite vary from one place to the other. And quite a long time ago, Shikazono compiled gold-silver ratios of epithermal type, low sulfidation epithermal type deposit. Almost always silver is much higher than gold, but through that ratio vary a lot. And also that gold-silver ratios in native electron grain quite different, but almost always silver is much higher in gold grain electron. That's the reason we call it electron. And deposit itself quite high silver so gold ratios. That's quite different from, for example, orogenic type gold deposit.
Thank you, Professor. Do we have any more questions? Going once? Going twice? If there are no more questions, Professor Tori, thank you so much. The past 3 days has been truly enlightening, not only for us graduate and undergraduate students, but also to geologists here in the Philippines who attended your virtual lecture. So we would like to present a small token of appreciation from the University of the Philippines National Institute of Geological Sciences for sharing your knowledge to us.
I should thank you to invite me over. Thank you very much. Thank you very much. Really, thank you very much. Thank you very much. Thank you very much.
So before we finally wrap up our event, may we request both our on-site and virtual participants. For virtual participants, please turn on your cameras. For our on-site participants, let us proceed here in front for a photo opportunity with Professor Hattori. So we would like again to thank Professor Atori for coming here in the Philippines, sharing your expertise and knowledge with us. So our virtual participants and our on-site participants, let's give Professor Atori a big round of applause. And we hope to have you next time, and we wish you safety in your journey. And also, we would like to thank all our participants, both on-site and virtual, for sticking with us for the past 3 days. I hope you've learned something in our lecture series, and we hope to be with you again during our next lecture series. So for participants, we would like to know your feedback or have your feedback. So please scan the QR code present in your screens, and your feedback will be highly appreciated as we continue to deliver these services. Also, as a reminder for our participants, as we inch closer to GeoCon 2022, the deadline for regular registration is on the 11th of November. This year's GeoCon with the theme Disruptions, Transformations, Geosciences at the Forefront will be held from December 5 to 7. The first 2 days will be conducted fully online, while the last day will feature a hybrid setup. Again, we would also like to thank once more the following groups and organizations who made this event possible: the Office of the Vice President for Academic Affairs of the University of the Philippines, the National Institute of Geological Sciences, the Society of Economic Geologists, the Geological Society of the Philippines, and the Rush Urgent Working Group. And with that, we conclude our World Expert Lecture Series with Professor Hattori. Thank you everyone for spending the past 3 days with us, and we look forward to see you again on our next webinar series. Stay safe and have a pleasant day ahead.